Okay, hello students and welcome to our second lesson on gases, and today we're going to look at the ideal gas equation. So the point of the lesson is that we want to consider the relationship between volume, number of moles and molar volume at standard temperature and pressure, which we call STP. We'll use kinetic theory of gases to describe and explain the behavior of gases, including those qualitative relationships between pressure, temperature and volume, and I appreciate that the kinetic theory of gases applies to ideal gases and solve problems related to the ideal gas equation. So if we want to look at properties of gases, there are four measurable quantities that we can influence: the pressure, the volume, the temperature, and the number of molecules. The first relationship we can look at is Boyle's law, and as you can see here, it's named after Robert Boyle, and as the pressure increased, the volume decreased. So we describe this as for a given quantity of moles of gas at a given temperature, the product of its volume, which is V, and its pressure, which is P, is constant. So P times V equals K, or a constant. It can be written as PV equals K, and this is an inversely proportional relationship to volume. So if we can express this in a couple of different ways as well, we can also rewrite Boyle's law as PV equals K, or a constant, or pressure equals proportional to 1 over volume, or P1 V1 equals P2 V2. So where P1 and P2 are the initial and final pressures, and V1 and V2 are the final volume, initial and final volumes of the gas. If we have a look at the relationship between volume and temperature, this is known as Charles's law. And here is the fellow that got around in a hot air balloon. So the volume of a gas is directly proportional to the temperature and extrapolates to 0 at 0 Kelvin. So therefore, we must do our calculations with gases in kelvins. We can write this as volume over temperature is a constant, or V1 over T1 equals V2 over T2. Now you can see that this is a directly proportional relationship. As one goes up, the other one goes up, or as one goes down, the other goes down. So the temperature, as I said, must be in kelvins. It does not work for degrees Celsius, and certainly not for Fahrenheit in this relationship. Now the next one is the volume and the moles of gas, and this is Avogadro's law. So equal volumes of different gases measured at the same temperature and pressure contain the same number of molecules. So this is a great thing. So you'll see a couple of different, I suppose, numbers for this. You'll either see 22.4 at STP or 22.7 at STP. And we'll just explain a couple of differences. A real gas is obviously different to an ideal gas. So often it will be 22.4, and this is at 1 atmosphere, which is 101.3 kilopascals, whereas at 22.7 will be at 1 atmosphere, which is, at 100 kilopascals. So 1 atmosphere is actually 101.3 kPa. So that's what this diagram is showing you here. Now, at a constant temperature and pressure, 50 mils of oxygen contains the same number of molecules as 50 mils of nitrogen or ammonia or argon. So measured at the same temperature and pressure, 1 mole of any gas has the same volume of 1 mole of any other gas. So we call this the molar volume of a gas. Now its value at STP, which is 0 degrees Celsius, and 100 kilopascals is 22.7. As I said, the other number you will see is at 101.3 kPa, and the volume will then be 22.4 litres. Now the pressure and temperature of a gas is also related. So this is Guy de Lussac's law. So the pressure and the temperature of a gas are directly related, provided that the volume and the moles remains constant. So we say that P1 over T1 equals P2 over T2. And temperature must be in kelvins. And you can see this summarized nicely here. So volume and pressure are inversely proportional, so that's for boil. So we have an inverse relationship here. If we look at Charles's law, as temperature is decreased, the volume decreases. So if I would put a blown up balloon in liquid nitrogen, for example, you would see that it shrinks. And then if I have a look at Lasac's law, temperature and pressure are inversely related, directly proportional. And Avogadro's law is that the number of molecules or the moles of the gas is directly proportional to the volume. So this can all be combined into what we call the ideal gas law, which is PV equals nRT. So the pressure times the volume equals the number of moles times a constant called the universal gas constant, which is the symbol R, times the temperature in kelvins. So we use this symbol R for the constant, and it's called the universal gas constant. So we can say that pressure times volume equals the number of moles over, number of moles times the temperature, which equals this constant rate for any gas. So pressure must be in kilopascals or atmosphere, volume in litres, N for number of moles. R equals our universal gas constant. This way I've given it to you in joules per Kelvin per mole, and the temperature is in kelvins for this example here. And this holds pretty closely when we're at low pressure, so less than 1 atmosphere. So if we have a look at a worked example, 10 litres of gas exerts 2.5 atmospheres of pressure at 200 Kelvin. So how many moles of gas are there? So we know that PV equals nRT, and let's convert to 253 pascals. So I thought I did some working there. It might turn up later. So 2.5 atmospheres. So just remember 1 atmosphere is 101.3 kPa. So I just multiplied this 2.5 by 101.3 kPa to get to my 253 kilopascals, because I gave you the universal gas constant in kilopascals. So we can then just multiply through and solve for N, because we are asking for the number of moles. So we're asking for this one. So the number of moles equals just that 2,350 kilopascals per litre, divided by 1,642 joules per mole, and that's going to be 1.523 moles. Now this is interesting that you can see that a 1 kilopascal then does a certain amount of energy or work per unit volume, and that's 1 kilojoule per mole. So a joule in this case is 1 kilopascal per mole. And that finally turned up. If we have a look now at another example, so what I've done here, I think I'm going to ask you to do 2 conversions. So we've got PV equals nRT, that's our ideal gas equation. We've got 1.5 moles of gas, so we've got that in a 10 litre container, so we've got a volume at a temperature of 25 degrees Celsius. We'll have to convert that to Kelvin. And how much pressure is there? So it's going to be this one we're asking in atmospheres and kilopascals. What I've done here is I've shown you another version of the universal gas constant, but that's the conversion factor for atmospheres. So remember 101.3 kilopascals per atmosphere, so you can see that we're about 100 times less than the one given to you in kilopascals. So we're doing this, so let's do the kilopascals one then. So we've got what do we got? The pressure equals 10, well, that's 10 litres, and then we're just substituting in and then solving for P. And that's it there. And let's have a look at it in atmospheres. And you can see that they're about a factor of 100 out, which is what you expect because of that conversion factor there. So the pressure in kilopascals is 371.6 kilopascals, and in atmospheres it's 3.67, so 3 2/3 times the normal sea level pressure. Now, ideal gases are imaginary gases. So remember, imaginary gases do have these intermolecular forces, and so they are going to decrease their volume, and they don't fit all the assumptions of kinetic molecular theory. So the gases do consist of tiny particles that are far apart relative to their size, and the collisions between gas particles and the walls of the container are generally elastic collisions in this theory. No kinetic energy is lost in these collisions. Gas particles are in constant rapid motion. They possess kinetic energy, the energy of motion, and there are no forces of attraction between the gas particles. So remember, this is our assumptions for ideal gases. And the average kinetic energy of a gas particles depends on temperature, not on the identity of the particle. However, real gases are a bit different to our model. So real gases do experience intermolecular attraction. So even remember, neon had those temporary dipoles which allowed those monatomic neons to stick to each other. And real gases do have some volume, and real gases do not have elastic collisions. So there are changes from the ideal behavior. So they are likely to behave ideally at high temperatures and low pressure, and then if the gas particles are a bit like neon, they're small and they're non-polar gas molecules. They're not likely to behave ideally if they are at low temperature and high pressure, and if the molecules are large and polar. So finally, can you please see if you can understand the goals for today's lesson? So have you been able to consider the relationship between volume, number of moles, and molar volume at STP? Use the kinetic theory of gases to describe and explain the behavior of gases, including those qualitative relationships between pressure, temperature, and volume. That's what, are they directly proportional or inversely proportional? And appreciate that the kinetic theory of gases applies to ideal gases, and solve problems related to that ideal gas equation PV equals nRT. When you're done, you can have a go at the mastery questions.